Hi, my name is Mudassar and in this video I will present our paper to appear in ICC 2020. The title of the presentation is Adaptive Millimeter Wave Communication Exploiting Mobility and Blockage Dynamics. This is a joint work with Maria and Michele from University of Padova and my advisor Nicolo from Purdue. As we all know, in order to satisfy the stringent requirements of future applications in 5G, the goal is to push the performance requirements of future wireless networks to the limits in terms of capacity, latency, reliability, density of devices, and so on. So millimeter wave is the key enabling technology in 5G to achieve multi-gigabit per second speeds, thanks to availability of large bandwidths on this millimeter wave band. However, there are several challenges faced in the design of millimeter wave communication systems. One such challenge is the high isotropic path loss as dictated by Free's propagation law and shown in this figure. We can overcome this challenge though by using large antenna arrays and narrow beam to focus energy in a desired direction, thanks to smaller wavelength which allows us to pack large number of antenna elements in a small form factor such as a handheld mobile device. The problem with highly directional beam is that in order to communicate, the beams of the transmitter and receiver need to be aligned with each other, which can be a source of severe overhead in mobile environments. To make things even worse, the signal is also more strongly attenuated by objects, building, grain, vegetation, which causes a high dynamic link quality and blockage of the signal. Therefore, in order to support mobility and compensate for high dynamic link fluctuation, we need to frequently realign transmitter and receiver, which requires the design of fast beam alignment and handover strategies to quickly recover the signal quality. To achieve that, in this work we will propose our data-aided scheme where base stations collect the measurement of users' mobility, propagation conditions, and build a map of the environment, as shown here. These maps then can be exploited to track the position of the users and perform beam alignment more efficiently. This is particularly interesting in a vehicular scenario as shown in this figure. For example, the mobility of the vehicle is bounded by constraints such as road lanes, speed, and therefore its position can be predicted fairly accurately to improve the beam alignment process. For instance, in this case, I can predict the forward movement of this vehicle and I can discard the blue beams from the beam alignment process, knowing that only the red ones are going to succeed. The base station can learn this mobility pattern from the previous interaction with the users. Another problem that I mentioned at the beginning is that the millimeter wave signal is very sensitive to blockages. For instance, there might be a vehicle coming from the other lane which blocks the line of sight signal, which causes the disruption of the communication. In this case, we need a mechanism to quickly detect the blockage event and perform handover to recover the communication link. This needs to be done autonomously without any external aid. So the question that we are going to address in this work is how to leverage the learned mobility and blockage dynamics to improve the process of the beam alignment, data communication, and handover in a fully automated fashion. Our contribution is designing a protocol to address this question. The general version of this work is currently under review in IEEE Transaction on Vehicular Technology and could be found at this archive link. Let's take a look at the existing literature. We have here listed two works which are closely related to our paper. The first work is based on multi-arm bandits. The authors in this work propose to use the GPS information of the user to reduce the overhead of the beam alignment. This work has practical limitation as well as privacy concerns. In addition, it does not leverage the mobility and blockage dynamics to improve the beam alignment process. Furthermore, it lacks the mechanism to detect blockages and to perform handover. The second work is based on partially observable Markov decision process model, where authors design a periodic beam alignment data transmission protocol. Similar to previous work, this work lacks the mechanism to perform blockage detection and to perform the handover. Furthermore, it does not utilize the data transmission feedback. In this paper, we will consider a Markov decision process model. So in this framework, we are considering for simplicity to base station and a vehicle following some mobility process along the road. The state of the system is given by the best beam currently associated with the user's location, the blockage state of the channel, and the ID of the serving base station. The actions available are the choice of whether to perform beam alignment or data communication or handover, and how to perform these actions. For instance, for how long should the base station perform data communication before receiving feedback, how much power should it use, and which beam should it use to communicate or to perform the beam alignment. The goal is to define a strategy that dictates how these decisions are taken so as to maximize the average throughput subject to an average power constraint. The challenge of solving this problem is related to partial observability. This is due to the fact that the state of the system is not perfectly known. In addition, the dynamics of user might be uncertain. The blockage and the best beam need to be detected under noise, which is another source of uncertainty. So how do base station optimize the decision-making process under such uncertainties? So in order to do that, we are going to propose a partially observable Markov decision process-based model. In this setting, the uncertainty in the state of the system is captured by the belief beta, which represents the posterior distribution of the state given all history of actions and observations collected. Given such belief, the serving base station chooses one of the available action according to the policy pi, which is part of our design. At end of each action, a feedback signal is generated by the user and sent to the base station, which, upon receiving the feedback signal, updates the belief following the base rule. Then we can write the expected throughput and average power matrix using Little's law, where R total is the total number of the bits delivered during an episode duration, which is the interval of the time until the user exits the coverage area of the base station and can no longer be served. Then the goal becomes of maximizing the total number of the bits delivered to the user subject to a total cost constraint. Since we have a constraint optimization problem, a natural way is to form the Lagrangian formulation of the problem followed by defining a value function of the Lagrangian problem. The goal then becomes of that finding a policy that maximizes the value function, which is the fixed point of Bellman optimality equation. An important note for the next derivation is that this equation can be written as inner product of a belief vector with a properly defined hyperplane, as shown here. This equation can be solved approximately using value iteration methods, but the complexity of this approach can be shown to grow doubly exponentially, and therefore it's not doable for any problem of practical size. One of the most promising approaches to overcome the computational challenge of solving PMDP is that of using the point-based value iteration methods, where the main idea is to restrict the value function optimization to a subset of the belief space. One then can see that the problem of finding the optimal value function in PMDPs can be reduced to finding the optimal hyperplane based on the observation I made earlier. The problem is that in the specific problem we are interested in, we have a cost constraint which requires to solve the dual optimization problem to find the dual variable. A brute force approach to do that would be to compute the value function for different values of lambda and then optimize exhaustively over such values of lambda. However, this approach is not efficient, it has a large computational overhead, and it is not exploiting the structure of the problem such as Markovian dynamics. Our contribution is that of defining a constraint point-based value iteration method that exploits a cost-reward decomposition and that avoids this brute force approach. So ideally, in order to optimize a dual variable, I want to be able to use a projected gradient descent method. But in order to do that, I need to get access to my cost metric, which is hidden in the Lagrangian value function. In order to recover that information, the proposed idea is to decouple a set of hyperplanes that represent the value function into two sets of hyperplanes, one associated with the reward metric, represented by alpha sub r, and the other associated with the cost metric, represented by alpha sub c. So following the value iteration updates, we can write the value function in the desired form as inner product between belief and new hyperplane for the reward minus lambda times the inner product between the belief and the hyperplane for the cost. This can be done iteratively and allows us to estimate the cost metric and adjust the dual variable at the same time scale as we optimize the value function. I am now going to show some numerical results. The results presented here are based on our general version, which has more practical assumptions about beamforming and mobility, such as 3D beamforming and 2D mobility. In addition, in the journal, we propose two heuristic policies to trade off performance and computational complexity. Nevertheless, both conference and journal version have same analytical model and same optimization setup. In the shown figure, we have on the x-axis average power consumption in dBm and on the y-axis spectral efficiency in bits per second per hertz. Notice that the abstracted model based on Markovian dynamics and sector antenna gain model is shown with the solid lines, whereas the evaluation with analog beamforming and Gauss-Markov mobility model is shown with the markers. You can see that there is a perfect match between the abstracted model and more realistic one, which proves the validity of the abstractions used in the analysis. In addition, the optimized policy obtained via the proposed constraint point-based value iteration method achieves near optimal performance, very close to the gene-edited policy which assumes the perfect state knowledge. Next, we show the performance of a baseline scheme which behaves similar to a conventional exhaustive search method, but with the exception of the blockage detection via exhaustive search. By comparing the performance of the baseline scheme with the proposed scheme, we can see a huge gap, which is due to the fact that the proposed scheme adapts to the specific mobility and blockage dynamics and uses the feedback optimally to improve the decision-making process. In the journal, we have more results about, for example, convergence trend, which are not presented here due to time limitation. The main message here is that the design of the adaptive policies that exploit local dynamics offers superior performance, and also the modeling abstraction work pretty well to represent the more realistic scenarios. To conclude, the design of future wireless networks require flexibility and adaptability to meet the demanding goal of 5G and beyond. I have here presented an application of this concept to design the adaptive communication for millimeter wave wireless systems. And we have shown that the theoretical models provide good insight to derive the practical design. So thank you for listening to my presentation.